Okay, welcome to our last online lecture for Equilibria. This one's going to be a lot shorter. I also changed the background, so it should be easier for you to read and watch along. We're essentially just looking at equilibria or equilibrium in one more way. And this is going to go back to thinking about our solubility rules. And we had our solubility rules that we memorized for double replacement, those things that would be insoluble or those things that would be soluble. Well, what we're going to learn in this particular unit is that was actually kind of a lie. Um, Everything dissolves a little bit. It's just we classify some things as insoluble because we can't actually detect with our eye that anything has actually dissolved into the solution. If we really wanted to determine that something had dissolved, we need like a gas chromatograph or a mass spec or an atomic absorption machine, something that could analyze it at a level that we aren't able to. So when we're talking about solubility equilibria, we will be working with ionic solids. And we know that when we put our ionic solids into water, they dissociate into our cations and our anions. Even those things that are technically classified as being insoluble do dissolve just a little bit. And so I have this first example here, barium sulfate. If you went to your solubility rules, you would say barium sulfate is insoluble. And we have even talked about it with proof that looking at their charges, because there's a really large charge difference between the barium and the sulfate, that means they have greater electrostatic attraction. And that's another reason that we said this is insoluble. But that's not actually true. It does dissolve a little bit. So we get this forward reaction occurring where our solid barium sulfate does dissociate a little bit into our barium ions and our sulfate ions. Well, what happens as soon as we build up just a little bit of that barium and a little bit of that sulfate, they start colliding with one another and they start reforming the solid. So then we get the reverse reaction occurring, the ions coming together in order to form the barium sulfate again. Well, eventually we'll reach an equilibrium, and you remember the criteria for the equilibrium is that the rates of reaction must be equal. The rate at which you're producing the products must equal the rate at which you're producing the reactants. And the other thing that criteria we have to meet is that the concentrations can no longer change. Well, once we reach that equilibrium using that criteria, we can write an equation reflecting that equilibrium. Now you'll notice here that we have a solid present here. So in this particular set of equilibria that we're going to be working on when we do our products over our reactants, there's never going to be anything on the bottom because remember we always cross out the solids. So once we get this equilibrium equation, then we can write an equilibrium expression for it. And instead of just our normal K, we're finally to that last K we need to study, and this is KSP. And the KSP is the solubility product constant. Notice in this particular case that we have left out the solid, because solids aren't part of the equilibrium. And so we're just going to be basing our KSP off the concentration of the barium and the concentration of the sulfate. And there's KSP once again, the solubility product constant. Now, there are a couple of different things that you can do with solubility equilibria. We can solve for KSP, which we're kind of used to doing already. And we can also solve for solubility. And what you need to remember is that word solubility also means molarity. So let's make sure we jot that in somewhere here. When we see the term solubility, that's also talking about the molarity or the concentration of it. So the two things we'll be looking for is, can we find the KSP and can we find the molarity or the solubility of the substance. So this first problem I have for you is to calculate the KSP of 1.0 times 10 to the negative 15th molar bismuth sulfide. And so the very first thing we're going to do, because these are ionic compounds, is we want to take our solid and we're going to dissociate it, because that's what ionic compounds do when we put them into water. They dissociate into their cations and their anions. A couple things I want you to be careful of is you notice that these aren't going to be one-to-one ratios. In this particular case, we have 2 bismuths, which are +3, and we have 3 sulfides, which are -2. And what else do we know? We know that the concentration of this is 1.0 times 10 to the negative 15th molar. Now, just like before, when we were working with our strong acids and they dissociated like this, we could establish the molarity of the hydrogen ions from the molarity of the strong acid. We're going to be able to establish the molarity of our cation and our anion from the molarity of our solid. I just noticed I have a mistake here I need to fix. We use the mole ratios. So if there is 1.0 times 10 to the negative 15th molar of our solid, well, if you look at your bismuth, for every 1 bismuth sulfide, we get out 2 bismuths. That's going to double the concentration. So we'll take 2 times our molarity, or we'll get 2 times 10 to the negative 15th molar bismuth. And with our sulfide, notice that for every bismuth sulfide we put in, we get 3 sulfides out. That means that concentration needs to be triple the amount, or multiply it by 3. So we get 3 times 10 to the negative 15th molar. Now they have asked us to solve for the KSP. So let's write our KSP expression. We have our bismuth. Now be careful here, it needs to be squared, and that's something you got to be careful of when you're looking at the concentrations. We not only doubled the concentration, but then we're going to square it down here when we're solving for our KSP. And for the sulfide, we're going to cube it. So our KSP is going to be equal to 2 times 10 to the negative 15th squared times 3 times 10 to the negative 15th cubed. And as you could probably imagine, this is going to be a pretty amazing KSP value. Go ahead and type it into your calculator, and you're probably actually not going to believe it when you see it. It is 1.1 times 10 to the negative 73rd. This would definitely classify as a small k problem if we had to do that. That's probably the smallest k we've seen so far. Well, why does this make sense? Well, we're working with something that in October we would have classified as insoluble, saying that it doesn't dissociate at all. And now here in March, we're saying that really is true based on the KSP value. It doesn't dissolve very much. Its K is a lot less than 1. So it is lying really far to the left to our reactant. So it kind of makes sense why we classify this as insoluble. We don't get very many ions from it. So this is one type of problem that you can do with solubility equilibria, solve for the KSP. The other type of problem that we can do is we can actually work back and solve for the concentration, find out what the molarity would be. And that's the next problem that I would like to show you. We want to calculate the solubility of copper 2 iodate that has a KSP of 1.4 times 10 to the negative 7th. So you can definitely see a difference in this problem because the last problem we were given a molarity and we were going for the KSP. Now we have the KSP and we're going back to the solubility. And if you don't like the word solubility there, just right over top of it, put a capital M so you remember that that's just talking about the molarity. Can't do anything until we know how this dissociates. So we'll take our solid and we'll dissociate it. We get 1 copper ion and 2 iodates. Now, in terms of molarity, we don't actually know anything about the molarity of this yet, except we do know a relationship that exists. And so we're going back to our algebra skills. When we don't know something in algebra, we set it equal to x. So we're going to make the molarity of the copper 2 iodate, it's x, it's our unknown. And we can establish a relationship between our solid and our copper ion. There's a 1-to-1 ratio. So whatever the molarity of copper iodate is, it must also be the molarity of the copper. So we can set it equal to x. And then we go out here and we look at our iodate. Well, for every copper iodate, we get 2 coppers. So that must mean we get, sorry, that's incorrect. For every copper iodate, we get 2 iodates. So that means we're going to double the concentration. So let's make it 2 times x, or 2x. Now, no problem is complete without our equilibrium expression. We have our copper, and we have our iodate. Remember to square the iodate from our coefficient up in our balanced equation. We do know our KSP this time. It's 1.4 times 10 to the negative 7th. We know copper is x, and we know iodate is 2x. Now, you're going to remember this from before. This is the part that drives me crazy because you forget to deal with your coefficient. So we have 1.4 times 10 to the negative 7th. This right here, 2x, and we square that. That is not 2x squared, remember. That is 4x squared times another x gives us 4x cubed. We're going to then divide our KSP by 4 and then take the cube root of that. And that gives us 0.0033 molar equals our x. They asked us for the solubility or the molarity of the copper iodate. X is also equal to the copper iodate. So we have our molarity or our concentration of it. So these are the 2 basic problems that you do. Pretty much everything can be worked out by either solving for a KSP or sometimes you have to solve for the molarity. And so I have just a couple more things that I want to talk with you about. The next thing we're going to look at is going back to some things that affect solubility and relative solubilities. And we're still going to be using these same types of problems here pretty much. So the common ion effect and solubility. The solubility of a solid is lowered if the solution already contains ions common to its solid. This is going back to exactly what we were doing with common ion back in acids. If there was common ion present, that immediately lowered the pH. It forced the reaction back to the reactants. Same thing happens here. We're going to lower the solubility because we're going to force that reaction back to the reactants again. The other thing I want to look at is what's known as relative solubilities. It's possible that you can talk and figure out how soluble something is you know, comparing two solids, and if the salts being compared have the same number of ions in them, then you can just use the KSPs to figure out who's more soluble or who's less soluble, and I'll show you an example of that. If the salts that you're comparing happen to have different numbers of ions, then you actually do have to do a little bit of math to calculate the molarities from the KSP. And so once again, anytime you see this word solubility, that's just another way for us to talk about molarity. So when we're talking about relative solubilities, we're talking about relative concentration. Who has the greater molarity, who has less molarity. So the first problem I would like to show you is to calculate the solubility of calcium fluoride in 0.25 molar sodium fluoride. So the first thing I hope you see on this problem is we've got fluoride here and we've got fluoride there. So fluoride is a common ion. And remember, anytime we have a common ion, the I changes. And what I mean is the I from ice has to be a little bit different. It's not going to be like our normal problems where we have something for the reactant and nothing for both of the products. This time we're going to have something. So let's go ahead and start and set up an ice chart. We're going to dissociate our calcium fluoride into a calcium ion and two fluorides. And we are trying to find the solubility of our calcium fluoride. So here, where the ice might help you a little bit, we don't care about this. Because it's a solid, it's not going to be anywhere in our equilibrium expression. So initially we have none of that. Now where this problem is a little bit different is we're going to have 0.025 of that. This comes from that additional salt, and notice it's sodium fluoride. That's something that is really soluble in water. So our change, we're going to have to make some calcium. Now be careful here, this has to change by plus 2x. That 2 is coming from our coefficient. That's something a little, you know, we haven't looked at in a while. We get x and 0.025 plus 2x. Now, as you can probably imagine, we're going to be able to ignore that plus 2x because look at our k value up there. It's to the negative 11th. That's much smaller than anything we used in our previous small k problem. So we're definitely going to get rid of this because we have a small k. Let's write our KSP expression. We have our calcium and our fluoride. Now be careful, fluoride is squared. It's been a while since we've had to put any powers on these things, put any exponents on them because we've been mostly dealing with those monoprotic acids. So watch out for that. Our KSP value is 4.0 times 10 to the negative 11th. Our calcium is X. And our fluoride, oh, you know what? I made a mistake up there, but I'm going to fix it now. It's 0.25 squared. 0.25 squared. Which I don't really know where I messed this up. I actually changed the number when I made up this problem and I typed it. So, okay. So we're going to get rid of that and we're going to work it with this. And I'm going to have to stop and grab my calculator and redo this math. So we have 4.0 second exponent negative 11, and we're going to divide that by 0.25 squared. And I think the calculator did not do my order of operations. correctly. Let me fix this real quick. There we go. 4 point. Oh, I'm sorry. I typed in a wrong number. Second exponent negative 11 divided by 0.25 squared. That gives us 6.4 times 10 to the negative 10th molarity equals X. Now, this will be the molarity of not only the calcium ions, but it is the molarity of the calcium fluoride as well, because notice between the calcium fluoride and the calcium, there's a 1-to-1 ratio. So this is the concentration of the calcium fluoride as well. 6.4 times 10 to the negative 10th molar. And then one last thing to show you was the relative solubilities. And so for each of the following pairs of solids, determine which solid has the smaller molar solubility. And see, I even threw the word molar in there this time. And so on our first pair, we have calcium fluoride versus barium fluoride. And if you notice up here, for A, the calcium fluoride versus barium fluoride. This is a little bit easier problem to work. This follows the first rule under relative solubilities. These have the same number of ions. Calcium fluoride has 3 ions, barium fluoride has 3 ions. So these have the same number of ions, and since they have the same number of ions, in order to find the smaller molar solubility, you look for the smaller KSP. Smaller solubility or molarity equals smaller KSP value. So in this particular case, our calcium fluoride is 4.0 times 10 to the negative 11th. It's going to have the smaller molar solubility because it has a smaller KSP. The reverse is also true. If it was asking you for the greater solubility, you'd look for the greater KSP. It works both ways. Now, on the second one, we have calcium phosphate versus iron phosphate. This one we cannot compare the KSP values because these things don't have the same number of ions. Our calcium phosphate has 5 ions in it. It has 3 calciums and 2 phosphates. Our iron phosphate only has 2 ions in it. It has the iron and the phosphate. When the number of ions are different, you have to calculate the solubility. So, ions are different equals calculate molarity. So we're going to come up with the molarity. And we have the KSP value. So this is like the second problem I did for you if you wanted to go back and review. So we're going to take our calcium phosphate. We'll dissociate it. We get 3 calcium ions and 2 phosphates. Now, remember we related our molarities to each other. So if this has a molarity of X, for every calcium phosphate we get 3 calcium, so its molarity needs to be 3X. And for every calcium phosphate we get 2 phosphates, so its molarity needs to be 2X. From here, set up your KSP expression. Now be careful because there's lots of stuff going on in this one. We're going to have calcium, which needs to be cubed, and phosphate, which needs to be squared. Our KSP is 1.3 times 10 to the negative 32nd. Now, careful here. We're going to put in 3x, and it has to be cubed. And we're going to put in 2x, and it has to be squared. And this becomes a little bit of a mess. So I'm going to write a few extra steps in here to help you. 1.3 times 10 to the negative 32nd. Look at this problem first, and what you're going to do, the mistake you're going to make is go, oh, this is 9x cubed. No, careful. 3 times 3 is 9. 9 times 3 is 27x cubed times 4x squared. Now, if you want to put that all together and simplify it, you get 108x to the 5th. So let me walk you through what you're going to do on your calculator for this. The first thing you're going to do is type in your 1.3 second exponent negative 32. Let's divide that by 108. Now, the easiest way to take your 5th root of this is type in 5, hit your math key, and then 5, and now you'll see you'll have a 5, a little x, and the radical. Now do second answer, and up it pops 1.6 times 10 to the negative 7th molar. 1.6 times 10 to the negative 7th molar equals x, which is the molarity of the calcium phosphate. So that's one molarity we have to look at. Now we have to do the exact same process for the iron phosphate, but you can already tell it's going to be a little bit easier because we have a 1-to-1 ratio. So if iron phosphate is X, then iron is X and phosphate is X. We write our KSP expression. Iron times our phosphate. This one doesn't have any exponents we need to add in. Our KSP is 1.0 times 10 to the negative 22nd. And we're going to fill in x to the both places. So if you want to go ahead and just go x squared there, you can. And all we're going to have to do is take the square root of this, which is 1 times 10 to the negative 11th molar equals our iron phosphate. Now that we have our two solubilities that we can actually look at, we see that the iron phosphate has a much smaller molarity than our calcium phosphate has. And so that, you know, it's deceptive because when you look up at their KSPs, if you had ignored the fact that they didn't have the same number of ions in them, you would have totally picked calcium phosphate in order to be the smaller molarity because it has a smaller KSP. But remember, that rule only works when the number of ions are the same, like we had in letter A. When you get to B, because the ions are different, you have to calculate the molarity. Now, I will let you in a little hit. You can always calculate the molarities every single time. You can always work every problem like we did on B, and you'll always get the right answer. So, you know, if you want to ignore that same number of ions thing, you can, because you can always calculate the molarities of them. So this one was a lot shorter, less than 30 minutes. Make sure you come to class ready to work.